Hi everyone, welcome to the next session of Earth Price Theories of Geotechnical Engineering 2. In last class, we have discussed about the various type of conditions for active earth pressure. Today, we will see one more condition for active earth pressure when the soil mass is effect of partially submerged condition. That means in some certain height, the soil is filled with some amount of bulk weight or dry unit weight, and some other portion of the soil is filled with water table or filled with water or partially saturation condition. In such situation, how we have to calculate the lateral earth pressure, we will see. If you observe here, this is the type of the retaining wall, and where here capital H is the total height of the retaining wall, and if you see here up to some certain height, up to this depth of H2, the soil is moist sand. That means small amount of wet content is, water content is present in the soil. Otherwise, in some situations they will give the soil as a dry condition. In those conditions, we will take, instead of gamma, we will take the gamma D. Again, if you see, after certain height H2, again after we are going linearly into the depth, again the weight of the soil mass, we are taking it as a saturated sand. Saturated sand means the soil what is available here, it is filled with water. That means the completely voids are filling with water. Hence why the unit weight of the soil mass, we are taking it as a gamma prime. Always we are calculating to ensure that when the soil mass is present in the water table, we have to take the unit weight of the soil mass as gamma. This is the condition they are asked for the while calculating any type of lateral earth pressure. Effect of partially submergence. That means one retaining wall is there. In that retaining wall, up to certain height, there is one layer of soil. In that particular layer, they will give the unit weight of the soil, as well as after certain depth, there is presence of water table. Due to presence of water table, the soil what is available here, the condition we are taking it as a submerged condition. For that submerged condition, we are taking the unit weight of the soil mass as a gamma prime. They will mention the point as a saturated sand, but you have to take while calculating the submerged condition. Why? Because the soil what is available here, the soil what is present here, it is filled with water. The soil will create pressure on the water. The soil will create pressure on the wall, as well as the water also will create pressure on the wall. And so we have to take the submerged unit weight. Again, if you see here, this is the diagrammatic representation of how the lateral earth pressure acting on the wall. If you see here, this is the pressure distribution diagram. See, this is the height of the retaining wall. And again, if you consider here, in this particular depth, while going linear to the soil mass, this is the portion of the soil mass acting on the retaining wall at a depth of H2. At this particular depth, if you want to calculate the horizontal pressure, that means nothing but sigma H2. That means horizontal pressure, the horizontal pressure at a depth of H2 equal to nothing but Ka into gamma into Z. Ka into gamma into, here they are given that point as H2. Hence we have to substitute Ka into gamma into H2. At this particular depth, the horizontal pressure is coming as sigma H equal to, or Pa equal to Ka into gamma into H2, where H2 is the height of this particular layer, and K is the coefficient of active earth pressure that we are calculating by using the coefficient 1 minus sin phi by 1 plus sin phi. And again, if you see here, after this layer, what is the layer present here? Again, the pressure creating in the same manner. That means the pressure, what is pressure available here, it is acting on the soil mass in this rectangular portion. Again, this layer won't act in this triangular portion. What is the here? The soil H2 has having some certain type of soil. That means either moist sand or clay or dense sand or very loose sand. Based on the type of the soil condition available here, the horizontal pressure it will may act here in a triangular portion. After this linear portion of the depth, the pressure what we are creating here, it will be transfer like this only. It will transfer like this only. That means it won't create again. It won't varying linearly with respect to the depth after changing of the soil strata. If you see here in this soil strata was changed. This is the first soil strata. This is second soil strata. In first soil strata, already we calculated the lateral earth pressure. While coming to the second strata, in second strata, the first strata load is acting like that only. Again, it won't to vary with respect to the linearity. Again, if you see here in a saturation conditions for saturated sand, again for saturated sand, see this is the top layer. Pressure acting on the bottom layer. Suppose if you consider this is first layer and this is second layer. For first layer, the horizontal pressure is Ka into gamma H2. Again, if you come to the bottom layer, in second layer, the pressure, horizontal pressure, what is acting here, the same pressure also will be acting in the bottom of the second layer. And again, if you see here, there is presence of saturated sand. For this saturated sand also, again from this depth H1, from this depth to up to bottom of the portion, this is the pressure again acting on this retaining wall. At this depth, the lateral earth pressure is different. Again, after this, there is one more presence of soil layer, soil strata. Again, in this, the horizontal earth pressure is different. Again, if you see here in this second strata, what is the soil having here? It is in a saturation condition, submerged condition. That means there is a presence of water table also available. Hence why there is again the presence of water pressure table also acting in this direction. This is the condition for partially or effect of partially submergence. That means for first two strata we are having the horizontal pressure of Ka into here where gamma is the unit weight of the soil mass, Ka into gamma into H2. This is the first layer acting on the soil mass at a depth of H2. The same pressure also will be acting on the bottom of the second layer. Again, if you see in this layer, the pressure what will acting on the retaining wall is nothing but Ka into gamma prime into H1. Ka into gamma prime into H1. That means nothing but horizontal pressure equal to vertical pressure into coefficient of earth pressure. That means sigma H1 equal to or horizontal pressure at a depth of H1 equal to Ka into gamma prime into H1. Where this gamma W into H1 is the unit weight of the water acting on the retaining wall. This is the condition how we are calculating the effect of partially submerged for the earth retaining structure. If you see here, the lateral pressure above the water table is due to the moist unit weight of the soil mass. Due to presence of water, there is small amount of capillarity will acting into the top layer. Hence why the soil we are taking it as a moist unit weight. And that below the water table is the sum of due to the submerged unit weight of the soil and the water pressure. And again, if you take below the layer, the pressure what was creating in the earth retaining structure, that pressure either due to the soil pressure as well as due to the water pressure. Why? Because the soil also will create pressure, the water also will create pressure. That pressure we have to calculate. And again, if you see here, where H1 is the depth of the submerged fill. If you see here in this diagram, for this diagram, the soil what is available here, this is submerged condition. That means it is filled with water, and the top layer is having with coefficient of earth pressure as well as moist sand. That is the parameter. And again, if you see here, where H2 is the depth of the fill above the water table taken to be moist. That means above the water table, the soil what is available here, that H2 we are taking it as a depth of the fill above water table, that is consist of moist. where gamma is the moist unit weight of the soil. That means moist unit weight of soil means some amount of water wet content is that bulky unit weight, moist unit weight we have to calculate. If they given the problem as specific gravity as well as void ratio, by using those parameters or properties we can determine the submerged unit weight as well as bulk or moist unit weight, where gamma prime is the submerged or effective unit weight. Gamma prime or submerged or effective unit weight of the soil mass. This is the condition how we have to calculate the lateral earth pressure for the earth retaining wall. This is same diagram I will explain again by using the coefficient of earth pressure with respect to the horizontal effective pressure to the vertical effective pressure. Suppose this is our retaining wall. Okay, this is our retaining wall and this is the horizontal ground surface, and this is the one layer and this is the second layer. Suppose this layer I am taking it as H2 and this layer I am taking it as H1. Okay, this is H1, this is H2. Again, if you see here, in H2, the soil is having bulk unit weight as gamma. The soil is having bulk unit weight of gamma. If you see here, the soil is filled with water, and that's why the unit weight of the soil mass we are taking it as gamma prime or gamma submergence. For this type of soils, we have to calculate the lateral earth pressure. In this bottom, I am drawing the pressure distribution diagram. For pressure distribution diagram, first I am taking this height. First I am taking this one vertical wall up to the height of the wall. Up to the height of the wall, I am taking one particular wall. If you want, now I am interested to calculate the how much amount of lateral pressure is acting at this layer, or at this particular point. For that particular point, I want to calculate the lateral earth pressure. That lateral earth pressure coefficient already we know. It is the ratio of horizontal effective pressure to the vertical effective pressure. That means coefficient of active earth pressure Ka equal to horizontal effective pressure to the vertical effective pressure. From the concept we are having horizontal earth pressure sigma H equal to Ka into sigma V, where sigma V is the unit, sigma V is the vertical stress. That vertical stress is nothing but how much amount of the soil is available here, that unit weight of the soil mass with respect to the depth of the soil strata. Now I am interested to calculate the vertical pressure at this particular point. That vertical pressure and horizontal pressure I want to calculate at this particular point by using this formula. That means by using the sigma H at A equal to, that means horizontal pressure at this particular point A equal to Ka into sigma V, that equal to Ka into sigma V is nothing but gamma into here height of the soil layer we are taking it as a H2. How means this is the pressure will acting on the retaining wall in this direction. This is the pressure acting on the retaining wall. Sigma H A equal to horizontal pressure at A equal to, this is the point Ka into gamma into H2. This is the pressure acting on the retaining wall due to this first layer. And again, if you see here, now I want to calculate the stress at this particular point. Now I want to calculate the stress at this particular point. For this particular point, the stress will acting due to the self weight of the soil available here, as well as our condition is submerged condition. Hence the soil will create pressure on the wall, as well as the water also will create pressure on the wall. In some situations, they will give the different type of soil properties at the bottom and top, at the top and bottom. In those conditions, what it will happen means the coefficient of earth pressure, it will may vary. Suppose here they will give the coefficient of earth pressure as Ka1. In second condition, they will give coefficient of earth pressure as Ka2. While calculating this coefficient of earth pressure Ka1, you have to substitute Ka1 into gamma into H2. The same horizontal pressure will act up to this. Again, if you consider this second layer, in second layer they are giving the coefficient of earth pressure as 2. In those conditions, we have to substitute Ka2 into gamma prime into H1. Again, gamma W into H2. Why? Because the soil is present the partially submerged condition. In our present condition, in a normal derivation, they are giving the same coefficient of earth pressure. Hence, there is no problem. Same coefficient of earth pressure we are considering. Again, if you see here, for this diagram, the same horizontal pressure will acting at this particular depth. Nothing but Ka into gamma into H2. Again, if you consider this vertical stress at this point B, that means again now I want to calculate the same horizontal pressure at this particular point. For this particular point, now I want to calculate the horizontal pressure. That means horizontal pressure at B equal to the horizontal pressure at B equal to the pressure. What is the first layer acting? The same pressure will act on the bottom of the retaining wall. This you need not to calculate. Well, because what is the linearly varying pressure? The same pressure is acting on the wall. That we will calculate. We will calculate the total partial submergence. That time we will consider. If now what I am doing, I am considering only this particular layer. For this particular layer, again how the pressure is acting? The pressure is acting again nothing but Ka into sigma V. Again the horizontal pressure at this particular point B only due to the second soil strata or soil strata at a depth of H1, that equal Ka into sigma V. Again sigma H at B equal to Ka into where sigma V is the gamma prime into Z, gamma prime into H1, gamma prime into H1. This is the one condition. Again if you observe here, see, this is the amount of pressure acting on the wall, Ka into gamma prime into H1, Ka into gamma prime into H1. The condition is in partially submergence. Due to partially submergence, again there is presence of water table effect on the retaining wall. Water also will create pressure on the wall. That pressure again we are taking as gamma W into H1. That water pressure also we are taking it as Ka into gamma prime into H plus gamma W into H1, where gamma W is the unit weight of the soil mass and the H1 is the height of this particular layer. This is how the horizontal pressure creating at particular point B only due to the second layer. Again if you substitute the first layer also, the total Ka into gamma into H2. This is the total horizontal pressure acting at this particular point B. This is the total horizontal pressure, how it is acting on the retaining wall. This is the calculation or analysis procedure for the calculation of lateral earth pressure when two types of soils are available. For these two types of soils, one soil is in moist condition, second soil is in a submerged condition. In some conditions they will ask, they will give here one coefficient of earth pressure, here second coefficient of earth pressure. And again if you see here, if there is no presence of water table, in those conditions we will neglect that water pressure effect. In those conditions we are having Ka into gamma into H2 again plus Ka into gamma into H1. Some conditions they will change the coefficient of earth pressure based on the type of the soil availability. This is the calculation for effect of partially submergence. This is most important. Maximum conditions they will ask in our end examination by this problematic, by this type of questions only. Okay. Next, we have seen all the parameters how we are calculating the effect of partially submergence. And if you see here, lateral earth pressure at base of the wall. Suppose if you see here, this is your retaining wall, and at particular depth, at total depth, after at particular depth H2, what is the total earth pressure that we have to calculate? The total earth pressure nothing but Ka into gamma H2, Ka into gamma prime into H1. Gamma W into H1. This Ka into gamma H2 is due to the first layer. And again Ka into gamma prime is due to the second layer. And again if you see here gamma W into H1, this is due to the pore water pressure. Due to the pore water pressure. If the soil is in a moist condition or dry condition, in those terms the gamma W into H1 we won't consider. Okay, this is the condition. Lateral pressure at the base of the wall when the soil mass is effect of partially submergence. This is the formula. Finally we have to remember. Okay, while calculating the problems you have to substitute these parameters in the problem. Directly we have to solve the values. Okay, this is the lateral earth pressure, how we are calculating for effect of partially submergence. Next we will see one more condition, effect of uniform surcharge. That means already in first class itself I have shown some abatements, some embankments, and in that I created one pavement structure. For this pavement structure there is a transportation of vehicles. That means either roadways or highways or railways are there. Due to this effect of submergence, the pressure, vertical pressure also will create on that wall. For this such type of problems, how the vertical pressure will be acting on the retaining wall, how the horizontal pressure also will lead to affect the pressure on the retaining wall, that we have to consider. Again, if you see here, this is the one more type of retaining wall. For this retaining wall, there is one type of pavement construction is there. In the pavement construction, there is a transportation of vehicles. For the transportation of vehicles, there is a uniformly distributed load acting on this soil mass. The uniformly distributed load we are taking it as Q into kilonewton per meter. And again, if you see here, this is the type of the soil available here. The type of the soil what is we are taking behind the retaining wall, we are naming it as backfill. The backfill we are taking as a cohesionless soil, and the unit weight of the soil mass we are taking it as a gamma. And if there is no presence of any uniform load or any such as load, preload on the retaining wall, for this calculation of earth pressure, how we have to calculate the earth pressure, that condition we know. The only difference is they are given the some amount of load acting on the retaining wall. That retaining wall, how much amount of load acting is nothing but we have to substitute the coefficient of earth pressure with respect to the uniform load, how much they are giving on the retaining wall. Suppose if you consider this same condition, for this condition to calculate the effective earth pressure, we know equal to sigma h equal to horizontal earth pressure sigma h equal to Ka into sigma b, vertical earth pressure. Okay, where sigma h equal to Ka is the coefficient of active earth pressure, Ka into where sigma b is the gamma into Z. Suppose if you